In the previous video, we are looking into the mathematical principles of the positional number systems, and particularly the binary system. Now it is time to build upon it and practice some key skills in binary and hexadecimal operations. The agenda for this session should appear here. Let's start with a paper-based but fully working binary adder, which is just a printed table. We will call it a register with printed binary weightings, the power of 2 from 1 up to 128. Real computers have very similar registers, they are just not made of paper. I have also a few tokens here, which will represent the values stored in the individual cells of this register. These cells are called bits. Our register consists of 8 bits, so it represents 1 byte. Let's now collect the task to complete. Just a moment. So our challenge is to complete the addition 117 plus 42. But in order to use a binary adder, we need first to convert the decimal values into binary. So let's start from 117 and just think what the binary representation of this number could possibly be. Could it contain the 2 to the power 7 or 128 bit? No, because 128 is too large. It simply wouldn't fit in the number 117. Maybe 64. Apparently, yes, 64 is small enough and it will fit within 117. Please note that for this method to work, you have to start from the most important bit, so the leftmost bit of the binary representation, and proceed to the right. Okay, once we have represented 64, we just need to find out what is the remaining part of our number, and because I'm lazy, I will use the calculator in my phone to find how much is it. 117 minus 64. It's 53. It's the remaining part, remaining portion of this number is 53. Does 53 contain 32, the 32 bit? Yes, absolutely. 32 is less than 53, so we have the second bit of our representation. So I will once again subtract 32. The remaining part is 21. Is the next bit okay? Yes, it is. The next bit is 16. So it is smaller than 21. Minus 16. The remaining part is 5. 5 means that the following bit, 8, is too big, but this bit is alright, 4. And I probably don't need to use the calculator, but minus 4, it's 1. 1 means this bit here. And here it is. This is the binary representation of 117. Let's now follow with the second number, 42. Of course, 128 is too big, 64 is too big, 32 is okay. 32 goes here. I don't even need the calculator to see that the remaining part, the rest of this number, is 10, so 16 is too high, 8 is fine. 10 minus 8 is 2, so that this will be the final bit. Okay, we are nearly there, because by just combining bits of the two numbers, I nearly have the representation of the sum of these two numbers, with one exception. This bit number 5 contains two or double value 1. Bits can only be not or 1, just two values. A bit cannot contain the value of 2. And the rule of resolving this binary adder in order to complete binary addition is that each time you find double bit in any double value in any cell, you just remove one of them and promote the other one to the next cell, to the higher cell of higher bit. The situation repeated. We again have double value here, so one is dropped, the other is promoted. Now everything is correct. We have the proper representation of our number. This representation would be 1 0 0 1 1 1 1 1. And now the next operation we need to complete is to convert this binary number back to the decimal. How we will do it? Just by adding these values, each value that has a bit switched on, together. So, what a lazy person, I will use my calculator again and complete the addition. 128 plus 16 plus 8 plus 4 plus 2 plus 1, 159. 159. I will make one more good use of this calculator to find out if our result is correct. 117 plus 42 equals 159. Wow, binary works. Let's reset our binary adder and concentrate on a simple operation of counting from 0. As you probably guess, an empty register represents 0, counting up to 15. So, counting is adding 1 to each consecutive number. So, this is adding 1 to 0, and this is how 1 is represented in binary. Add 1, but wait a moment, we have double value here, so 1 is dropped, 1 is promoted, this is 2. Add 1, this is 3. We have double value now, so 1 is dropped, 1 is promoted, again double value, 1 is dropped, 1 is promoted, this is binary 4. Add 1, binary 5. Add 1, drop and promote, binary 6. Add 1, binary 7. Add 1, okay, drop, promote, drop, promote, drop, promote, binary 8. Add 1, binary 9. Add 1, drop and promote, binary 10. Add 1, binary 11. Add 1, drop, promote, drop, promote, binary 12, add 1, binary 13, add 1, drop, promote, binary 14, add 1, binary 15. Task completed. We could add one more drop, promote, drop, promote, drop, promote, drop, promote. This is binary 16, but 16 is beyond our operation because I will now use a blank sheet of paper to write all binary numbers from 0 to 1111 or 15. 0 is easy. Now adding 1 to the last bit, 1 and all the others 1 are zeros. Adding 1 again would make the value of 2, so it reverts to 0. As we did with the tokens, 1 is dropped and the other is promoted. We call this promotion carryover, so 1 is carried over to this position and 0 is rewritten. The next addition is easy. The next one, 1 plus 1 is 0, carry over 1. 1 plus 1 is 0, carry over 1, and 0 here. Adding 1, not a problem, just rewriting everything else. 1 plus 1 is 0, carry over 1, 1, 0. Adding 1, 1, 1, 0. 1 plus 1 is 0, carry over 1, plus 1 is again 0, carry over 1, plus 1 is 0, carry over 1. Now, plus 1, 0, 0, 1, 0, carry over 1, 0, 1, 1, 1, 0, 1, 1 and 1, it's 0, carry over 1, plus 1, 0, carry over 1, and 1, plus 1, 1, 0, 1, 1. 1 plus 1 is 0, carry over 1, 1, 1, and the final addition. Okay, I can now add here the decimal representations of each number, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. But I also would like to show you some interesting pattern that was created here. If you look at the rightmost bit, you will see a clear pattern. It's 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, and so on. The second bit has 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. Then we have 4 zeros, 4 ones, 4 zeros, 4 ones. And again, 8 zeros, 8 ones. And you know what? If you would like to extend this array of numbers, this table, the next thing would be to add 16 zeros at the bit number 4, counting from 0. Remember, 0, 1, 2, 3, 4. It's not a fifth, it's a fourth, the fourth bit. So 16 times 0, then we would have to rewrite the same block once again with 16 ones. Then 32 zeros, 32 ones, and so on. This pattern would extend to infinity. But the important reason why I concentrated on writing the numbers from 0 to 15 is because in this way we got a very handy table showing the representation of consecutive digits, and you might think I do the same thing as here, that I just repeat, but no. I am now writing the digits of the hexadecimal system from 0 to F. F represents 15. Now I can set the title for this part of the presentation, hexadecimal digits, and of course the binary representation. But you might ask why anybody would like to use hexadecimal system, as it is not in everyday use, so it's not very practical, and computers use binary, not hexadecimal. I will show you why. We will now convert between decimal, hexadecimal and binary, but we will concentrate on converting really big numbers. And I will write a long binary number. I will write a 16-bit long binary number, and I will then convert it first to hexadecimal and then to decimal. Let it be something like this: 1 0 0 1 1 1 0 1 0 0 1 1. It's a totally random sequence of zeros and ones. But if we divide the sequence into groups of 4 bits, okay, a 16-digit number divides into 4 groups of 4. And as you can see in our table here, 4 bits represents exactly 1 hexadecimal digit. So I can take the first group here. I will take black pen. The first group here is 0011, and I will just convert this 4-bit short binary number into its hexadecimal representation. So I will, just to make things easier, I will write weightings, binary weightings above these digits, 1, 2, 4, 8. And you can see that I have 2 and 1, it's 3. Again, 1, 2, 4, 8. It's 4 plus, 8 plus 4, it's 12, plus 1, it's 13. 13, it's a double digit. But it has its representation in hexadecimal. From 0 to 9 it's like decimal, then 10 is A, 11 is B, 12 is C, 13 is D. So my next digit is D. Then 1, 2, 4, 8, it's 8 plus 1, it's 9. And you know what? The last digit, 1010, I won't even calculate. I will just use our lookup table here. 1010 is exactly here, and I can directly read that the hexadecimal representation of this value, 1010, is A. Done. In most computer programming languages, this hexadecimal value would be written as OXA9D3. OX is just a prefix, it's a special sequence of initial characters that allow the compiler to distinguish a hexadecimal value from any other sequence of random characters. Now, let's convert from hexadecimal to decimal. The weighting of this value is 1, then this is 16. 16 squared is 256. 16 to the power 3 is 4096. One possible method would be to take the value of this digit, which is A or 10, and multiply it by 4096, plus 9 times 256, plus 13 times 16, plus 3, and we would get a correct result. But there is another method which doesn't require us to remember these weightings powers of 16, and this goes like this. Take the first digit and its decimal value, which is 10, multiplied by 16, plus the second digit, it's 9, and multiply everything by 16 plus the consecutive digit and its decimal representation, it's 13, multiply all this by 16 and plus the final digit. Please note that this, and this are our hexadecimal digits. I will use my calculator again to do this simple calculation. 10 times 16 plus 9. In this calculator it's enough to press equals to close the bracket, times 16 plus 13 equals times 16 plus 3 equals. The result is 43,475. It's quite easy to notice that conversion from binary to hexadecimal is quite easy. Conversion from hexadecimal to decimal, it's much more complicated. But actually the reason why we most often use hexadecimal number is because the conversion between hexadecimal and binary is so easy. Let's go the other way around now. So from decimal to binary, but with an additional stop in hexadecimal. I will not take a very big number. I will just take what we started with today, 117, and it's hexadecimal 0x. Just a reminder, this is a prefix used by programming languages to distinguish between hexadecimal representation and anything else. So after this 0x, we will have hexadecimal representation of decimal 117. I will use calculator once again. 117 divided by 16, it's 7 and some fraction part, so there is 7 whole 16ths that can be fitted inside 117, and the rest, if I subtract 7 and get just the fractional part and multiply it by 16, I get 5. So 7, 5, this is the representation, hexadecimal representation of 117. And now the second stage, 7, 5, I will just write two groups of 4 bits representing both hexadecimal numbers. So, with my experience, I don't really have to think much about it. 7 is 0, 1, 1, 1, 5 is 0, 1, 0, 1, but of course you can always remember about these binary weightings. There are only 4 binary, 1, 2, 4, 8, there are always only 4 binary weightings for a 4-digit binary number, so representation of 5 is 4 and 1, and representation of 7 is 4, 2, and 1. Time to give a short summary of this session. It is important to understand binary because this is what computers really do, and you have to not only understand how they do it, but also quite many occasions as programmers you will have to work directly with binaries, and understanding them is essential. Binary is easy, but not very practical because binary numbers are terribly long. And this is where hexadecimal comes very helpful because it is concise. It is, in fact, shorter in notation than decimal numbers, and at the same time very easy to convert from and into binary. Conversions between decimals and the universe of binary and hexadecimal are a bit more difficult, but quite surprisingly, you will not have to do them too often in your work as a programmer. Once you are on the binary side, you will really need decimal values, and the reason why is you can use hexadecimal. Stay tuned, there is some extra practical material starting in a second. And the premium practice part, addition 178 plus 51, everything written. We will not use tokens, we will not use printed binary adders, just writing. First step, 178, how much is it hexadecimally? Let's take the calculator. 178 divided by 16, it's 11. 10 would be A, 11 is B. So it's a hexadecimal B minus 11 equals just fractional part. When I multiply this fractional part by 16, sorry, I get 2. B2, it's the hexadecimal representation of 178. 51 hexadecimally. 51 divided by 16, it is 3 and some fractional part. Minus 3 equals just this fractional part multiplied by 16, it's 3 again. 3, it's the hexadecimal representation of 55. Now I will take these 4 hexadecimal digits and I will separately convert them into binary to create the binary representation of the whole numbers. So, binary representation of B, that's 11. 11 I will start from writing small binary weightings here. Okay, definitely 8 fits well within B or 11, so it's 1, but not 4. 8 plus 4 would be 12, too much, so here we have 0. Now, yes, for 2, 8 plus 2 is 10. We still have 1 up to 11, so now 8 plus 2 plus 1, it's 10, 11, B. So that's the representation of the first hexadecimal digit. And just after this first digit, I will write the representation of hexadecimal 2, and that's easy. 2, no 8s, no 4s, 1, 2, no 1s. So 0, 0, 1, 0. That's the representation of 2. So we have this representation here. And below I will write the representation of 51. These are 2 hexadecimal 3s. So 3, it's 0 for 8, 0 for 4, but 1 and 1, 2 plus 1, it's 3. So that's 1 3, and another 3 will be also the same thing. So that's hexadecimal 3 3, binary 0 0 1 1 0 0 1 1, decimal 51. Underline everything, and now we do the addition. 0 plus 1, it's easy, it's 1. 1 plus 1, it's 1 0, okay? 1 plus 1 is 1 0 in binary. This means that I can only put a 0 here, and 1 must be carried over to the next position, or as we called it in whilst playing with tokens, promote to the next position. The next position is currently 0 plus the one which was carried over. It makes 1. 0 plus 0 is 0. 1 plus 1 is again 1, 0, and 1 will be carried over, so I put 0 here. 1 is carried over, but note another position is 1 plus carried over 1, so 1 plus 1 plus 1, it's 1, 1. 1 plus 1, it's decimally it would be 3, binary it's 1, 1. So this time I will put 1 here, and additional 1 will be carried over. The next position is 0 plus 1 from the carry, it's 1, and 1 plus 0 is 1. I have the binary result now. We'll now convert it to hexadecimal. So the first digit is 1110. It's 8 plus 4 plus 2. 8 plus 4 is 12, and plus 2 it's 14. Wow, 14. A, B, C, D, E. That's hexadecimal E. And now 0, 1, 0, 1. It's no 8s, but we have 4 and 1. It's 5. So our result hexadecimally is OXE5, which is converted to decimal. 16 times E is 14, so that's the value of E, plus 5. Let's use the calculator for this calculation. 16 times 14 plus 5 equals 229. And the final check whether the binary calculation are working or not. 178 plus 51 equals, yes, success! 229. Binary is working again. Thank you for watching. I hope you got some really useful skills working with binary and hexadecimal numericals. I invite you to the next video, in which we will be discussing binary representation of negative, or to be more precise, signed numbers. And you know what? As software developers or game developers, you should really ensure that your calculator can do the same thing as mine. 178, second function hexadecimal, B2, second function binary, 10110010. It's everything here.